Assalamu alaikum students, welcome to the new lecture of engineering drawing and graphics course, and in this lecture we will be talking about the interchangeability, that what is interchangeability, how it is related to the tolerance, and why tolerance gives us the option of interchangeability, which is an advantage in the manufacturing processes. So tolerance representation types, that's what we are going to discuss, and we are going to discuss the type of fits because in the last lecture we started discussing the threads and screws, and we discussed different type of assemblies also, different type of assemblies. So now we are going to be a little bit more specific and define the type of fits, what are fits and how are they all related to different tolerance types and the interchangeability. So let's move on. So geometric tolerance, what is geometric tolerance? As we already discussed this term tolerance, we established that no part can be practically manufactured to the exact dimensions. This is what it says right here. And tolerances are used to control the variations that are going to be on the manufactured part. So we already discussed that, and it is the amount each part can vary depending upon the function of the part and assembly. So it gives us a type of a you can say that is the error management, if you would like to call it the error management from the allowed dimensions. Then tolerance dimensions control the amount of variation on each part of an assembly, and when different parts are assembled they must fit together and function correctly. So this is what we basically covered in the last two lectures, that tolerances are defined for a specific part. For example, let's say that this is our part and this is one dimension of that part. Let's say this is the width of that part. So we cannot exactly manufacture, let's say that the width is 0.5 inches. We cannot attain 0.5 inches perfectly. So what we do, we specify two limits, upper limit and lower limit for this dimension, and we apply those limits on this dimension, and we get a range of dimension in which our width can be manufactured, our part can be manufactured according to a range of width, and that will be the acceptable part. So this is what we already covered, and these are the statements that we already stated. So what is tolerance and what is interchangeability? Interchangeability is basically replacing a part. And how does tolerance is related to that? Because tolerance allows this interchangeability. The one simple example is that of a light bulb, that if let's say you have a light bulb at your home and it gets fused, and nowadays the light bulbs have thread at the rear end. So if this light bulb gets fused, you can actually replace this light bulb in the holder that is installed, and that is the simple example of interchangeability, the bulb and the holder. The holders remain the same, but the bulb can be changed whenever it stops working. Whenever the bulb stops working, it can be changed immediately. So this is a simple example of interchangeability, that when a part stops working or wears out, or it is not functioning according to the required standards, then it can be replaced. So that is interchangeability, and tolerances does allow that interchangeability, because in this example if you are changing a bulb in your holder, you will be just making sure that there are threads at the end of this holder, and because the holder is threaded, so there should be threads on the end of this bulb. So this will be our main concern. We will be not concerned about the fitting, that how will that fit in the holder, because all the bulbs are according to a certain standard. The threads on the bulb are standard, and those standards are according to a certain tolerances that we already covered in the last lecture, that we specified that how are different threads, the metric and the Acme threads used, and how are different type of tolerances applied on those threads. So you will be the least concerned about the type of threads and how will it fit in there, because you already know that you have a threaded holder. This is a threaded holder. This is a threaded holder, and we will use a threaded bulb to fit in in this holder. So you will not be concerned about the fit, but it will automatically fit. You will just have to roll that in the holder. So this is one example, a simple example of interchangeability in which we use a bulb and a holder example, which can be easily replaced whenever the bulb stops working or is not functioning anymore. So that is interchangeability, and interchangeability is actually an interchangeable part is a mass produced part. It is produced in large number because it is getting replaced every now and then, and it is also called a replacement part. So this is the simple example of interchangeability. Another example is that of a spark plugs in an engine. You see these devices, these are called spark plugs. And their function in an engine is to provide a spark. If this is a spark plug, then their function is to provide a spark whenever there is an air fuel mixture, concentrated air fuel mixture. So this spark plug provides a spark to create a blast inside the cylinder, create a blast, and as a result of that blast the piston goes downward, and here to the crankshaft, it rotates the crankshaft, and that energy is similarly transferred to the wheels of the vehicle. So the spark plug is another example of an interchangeable part, because whenever the spark plug is not functioning, we can easily replace that in the engine. It is very easy to replace a spark plug in the engine. So that is another example of an interchangeable part. It is also a mass produced part, and it is also a replacement part. There are tons of example. For example, if you have a tire on your vehicle and the bearing starts a certain type of noise that you will hear, so the bearing is then said to be is about to be replaced. So that is also an interchangeable part. So if your tires are worn out, if your tires are worn out, then you can also replace your tiles on your vehicle. So that is also an interchangeable part. So a vehicle is a good example where you can find several examples of interchangeable parts, that how those parts can be replaced, and then the vehicle will function perfectly. So the tires, the bearings, the clutch plates, the spark plugs, these are some examples of interchangeable parts in a vehicle. So tolerancing and interchangeability, how is a feature on an interchangeable part dimension? How will we dimension those parts that are interchangeable? Because they are interchangeable, they are going to be replaced again and again. So they are according to be a certain type of tolerances that are going to be assigned to those parts, because we already said that we cannot manufacture a part according to its exact dimensions. So the feature is not dimensioning using a single value. This is what tolerancing is, but a range of values. So if this is the size dimensions and the basic size, for example, what does this mean? This means the upper limit. If let's say the dia, if this is the diameter of this cylinder, then there are two limits to this diameter. One is the upper limit and one is the lower limit. The upper limit is 2.007 and the lower limit is 2.003. So now there is this range defined for us to manufacture this cylinder according to these dimensions, and we do not have one dimension, but there is a range of values now. So we can actually manufacture this cylinder according to these range of values. And let's say if our manufactured part is 2.005, so it lies in this range. So this is correct, and it will be easy to fit this cylinder whenever we want. But if let's say if the desired dimension, if the manufactured dimension is 2.008, then it is incorrect, because if this cylinder is about to be fitted somewhere, then this dimension is not acceptable because it does not lies in this range. So this is what we do. We whenever we are talking about manufacturing an interchangeable part, so it is better to assign tolerances to them and a range of dimensions, because it will be easy for us both to manufacture it, but it will also be easy to fit it somewhere whenever it is required. So, tolerancing or interchangeability or tolerance is the amount of size variation that is permitted. It is the permitted size variation. You can choose a tolerance that specifies a large or a small variation. For example, the size limits, the upper limit is 1.005, the lower limit is this. So, you can actually calculate the tolerance. You simply subtract the lower limit from the upper limit, as you can see. So the over tolerance, that is 0.011 in this case for these dimensions. So calculating tolerance is simple. Then we have a question that why do we want a part size to be controlled by two limits? Why not just one limit? So it is necessary because it is impossible to manufacture parts without some variation, and these rated limits are a form of quality control. So by just assigning one limit, for example, if we say 5 inches and I say that it is 5.02, that is the allowed limit on this dimension. So this becomes still a little bit difficult. It is allowed, it is a certain, it is practiced, but it then becomes difficult because let's say if the allowed is 5 inches and I get into the range of 4.90, let's say, then this is not acceptable. So it is good to give tolerances in the both directions, in the positive direction and in the negative direction, so that we can have a maximum and a minimum value, and it will help us with the quality control also. So choosing a tolerance for your design whenever you are designing something. So how will you choose your tolerances? So whenever you specify a tolerance with a degree of accuracy that is required for a design to work properly, you are actually giving not now working with a single dimension, but you are actually working with multiple dimensions. So these range of dimensions are now actually allowing you a certain amount of error. So define these ranges so that are accurate, that is required to design our to work properly. So the main function is at the end the function of a part, that for what purpose that part is going to be manufactured. If it is manufactured, if it is going to fit somewhere, then that function, that is if it is going to fit somewhere, then you should assign tolerances according to that fit, and we are going to talk about the fit and tolerances in the coming slides. So first you have to assign the tolerances according to the design, that what is your design, and then choose a tolerance that is not unnecessarily accurate, that don't unnecessarily use very tight tolerances, or don't unnecessarily use very loose tolerances, but choose them according to the design so that your design will work properly. So there are two set standards, because whenever we are talking about something in the engineering drawing, we have standards, and according to the two most common standards agencies, there are also tolerancing standards. So the American National Standard Institute, the ASME, and the ISO are the two tolerancing standards that are majorly used. So the important terms are the in the tolerancing. Whenever we are tolerancing, we use some important terminology. So we should be aware of these important terminologies. And one is the basic size. What is the basic size? The basic size is the theoretical size used as a starting point for the application of a tolerance. That what is the starting dimension? For example, we said in the earlier example that the starting dimension is 5. So that is my basic size, or the nominal dimension from which tolerances are derived. Then the actual size, this is the size that is after the machining, that when we machine a part, then what is the size of that certain part, and that is the actual size of the object. Then we have limits, the maximum and the minimum size shown by the tolerances dimension, and the allowance. As I discussed in the classroom, that in our physical lecture I said that tolerance is for a specific part. For example, if this is a part, then if this part has a certain width, then if say the width is 5 and I assign 2 dimensions, then this is for this specific part. These are the tolerances that are specific to a part. But let's say if this part is to be fitted in a hole like this, then the minimum clearance, that is the minimum clearance, the minimum clearance or the maximum interference. For example, the shaft, if we say this is a shaft and this right here is a hole, so the minimum clearance or the maximum interference between parts or the tightest fit between two mating parts is called the allowance. So allowance is between two mating parts. It is between two parts that are going to be fitted, and for example this hole and a shaft, these are two parts, and tolerance is for a specific single part, but these tolerances are according, if that part, for example the shaft, we assign two tolerances to a shaft, so these tolerances should be in accordance to the hole that is being fitted in. So allowances between two mating parts, and they can be, there can be a clearance between the two mating parts, a clear space, and there can be interference between two mating parts, and there can be both. So we will see the allowances, the type of allowances, the limits and fits in the coming slides. Maximum material condition, the condition in which the material is maximum, and we discussed that for a shaft, that will be the maximum diameter of the shaft. So in case of a hole, that will be the minimum diameter for a hole, and in this case it is the maximum diameter, and in the whole case it will be a minimum diameter. So this is the maximum material condition, and again the maximum MMC of an external feature such as shaft is the upper limit, and MMC of an internal feature such as a hole is the lower limit. Then the least material condition is the condition which the material is minimum, and that in this case is the lower limit for the external feature, that is the lower diameter of a shaft, and the maximum diameter of a hole. So the upper limit for a hole, that is the internal feature. So tolerance representation types, tolerance methods to present tolerance. There are different methods: limit dimensions, plus minus tolerances, and page or block dimensions. We are going to discuss them one by one, that how we are going to represent tolerances. So limit dimensioning is using two dimensions, that is the upper limit and the lower limit. So this is the upper and lower limit on this size, the upper and lower limit on this shaft, the upper and lower limit on this hole, the upper and lower limit on this angle, and the upper and lower limit on this hole right here. So these are called the limit dimensioning. So the plus minus tolerances, in which the tolerances are given as plus minus some value or plus minus two different values. So there are two types, bilateral and unilateral tolerances. So let's look at them. Bilateral tolerance, in which there are two different plus minus symbols, and the plus minus approach is used when the two variations are equal. For example, let's say these are the bilateral tolerance, in which the tolerances are in both directions, both in the upward direction and both in the negative direction. As you can see right here, it is plus minus 0.2. So 22 plus 0.2 and 22 minus 0.2. So 22.2 and 21.8 is the range that is defined by this plus minus 0.2. Similarly, it can be different. It can be plus minus 0.1 and minus 0.2. It cannot be the same value, and similarly it can be plus minus 0 degree and 5 minutes as for this angle. So these are bilateral tolerances in which the tolerances go in both the upward and the downward direction. For example, if we look at this diagram of a shaft, so if this is the basic size, up until here, so the lower limit is the minimum limit and the maximum limit is the upper limit of that tolerances, and this is the basic size, the one to which the tolerances will be assigned. Then we have unilateral tolerance in which the tolerances are in one direction. For example, if you see here 32, then the upper limit is 0 and the lower limit is minus 0.02. In this case, the upper limit is plus 0.02 and the lower limit is 0. Similarly, you can see from these dimensions right here, the tolerances is only in one direction. The one, for example, here the plus is 0, the negative has some value. Here the plus is 0.1, the negative is 0, and here the plus is 0 and the negative is 0.2. Similarly, we have one basic size, and that basic size will either have a minimum limit if the tolerance is in negative, or it can either have a maximum limit if the tolerance is in the positive value, just like this. Other approaches are to tolerance specified in a tabulated manner. For example, if this is our part, a cylindrical feature, and these are the different diameters on this part, so we can actually assign tolerances not here, but in a table that is separate from that drawing, and we can say that on dimension A, apply these two tolerances, on dimension B, right here, apply these two tolerances, and on dimension C, apply these two tolerances, and then on dimension D, apply these two dimensions. We can also make out separate notes that tolerance can be specified in a general way to cover a wide range of dimensions. For example, except where otherwise stated, general tolerance to be plus minus 0.1. If it is not stated with the dimensions, then it can be stated separately in the form of a statement just like this. Or we can say that the general casting tolerance, casting is a manufacturing method, we discussed that general casting tolerance is plus minus 0.3. So it can also be stated in the form of a note. It is not necessary that tolerances are always assigned to a dimensions, but it can be stated in the form of a note or in the form of a table like this. Then the degree of fitness between two mating parts is called a fit, that how two parts fit together. So there is a clearance fit. In clearance fit there is also gap between two assembled parts. So here, right here, if this is a hole, this is a shaft, so there will always be clearance. There will always be space between these two mating parts. So that is called the clearance fit. Clearance fit allowance is positive, so the allowance of the clearance fit is positive. Allowance, as you can see, can be calculated by subtracting the size of this hole from the size of this shaft, so we will get a positive number. Then we have interference fits. The interference example is very simple. For example, the shaft and the bearing example that are attached to your vehicle tire are an example of interference fits, because the bearing is tightly fitted on the shaft. So in which the shaft is always bigger than the hole into which it fits, interference fits always overlaps and are mainly used to press fit. The two mating parts are pushed together and require no fasteners. So here, right here, now you can see that the hole size is less than the shaft size. So this is an interference fit where we want a press fit, where we want these two parts to not move relative to each other but to stick to each other. This is also a type of fastening, as you can see, because the two parts are now overlapping in size. And interference allowances are always negative. For example, if you subtract the shaft size from the hole size, then it will come out to be a negative number. The allowance will be negative. Then there is transition fit, and in transition fit the clearance can be positive, the clearance can be negative, and transition fit exists when the maximum clearance is positive and the minimum clearance is negative. Transition fits are used only for locating a shaft relative to a hole where the accuracy is important, but either a clearance or an interference is permitted. So transition fits are used to locate a certain features. For example, the best example of transition fits are the piston and cylinder, that are used in the internal combustion engines. So the piston, as you know, can freely move up and down in this cylinder, but it also cannot permit any exhaust gases in this cylinder. In this direction, it actually pushes it upward out of the exhaust ports. So similarly, it sucks the air fuel mixture, but the air fuel mixture does not go downward. The interference fits right here actually allows it to just remain above the piston in this region right here and does not seep into these regions. These are the examples of an interference fit where the as it is stated right here, the maximum clearance is positive and the minimum clearance is negative. So it is also used for locating a shaft relative to a hole where the accuracy is important, but either a clearance or an interference is permitted. So here interference is permitted, but it also locates the cylinder in this piston. It also locates, sorry, this piston in this cylinder, and it does not actually allows it to move or vibrate this piston in this cylinder. So this is the type of a transition fit, as you can see from this diagram. This is the maximum interference and this is the maximum clearance that they can have. So it actually lies between the clearance and the overlapping fit that we just saw. And transition fit allowance, as you can see, as it changes between the two fits, it can either be positive or it can either be negative. So what are some examples of these fits? So you can relate them to your daily life. So the clearance fit example is your lock and key, your door inside a door frame, and the coin. If you have played some video games, the coin that you used to put in a slot is an example of clearance fits. And the interference fit example are the pin in a bicycle chain, the hinge pin, and the wooden pegs that, and a hammer toy. The wooden pegs that we used in our pads that we call the char pai. We use wooden pegs to tighten the wooden pegs with the handles like this. So we use wooden pegs right here. So they are example of interference fits. The pin in a bicycle chain that we use, for example, the chain that there is a certain amount of, there is a certain pin. So this is also an example of a interference fit. Then the transition fit example is the piston and the cylinder inside the internal combustion engine. Then to determine the fit, there can be two types of fits. One is the loosest fit. So the loosest fit is between the smallest shaft. It can be between the smallest shaft and the largest hole. That will be the loosest fit, as you can see. And the tightest fit can be between the smallest hole and the largest shaft. So that will be the tightest fit. So these are the this is a method to determine what type of fit we have. So if we have this combination, if the hole is large, the shaft is small, then we will have loosest fit. If the hole is small and the shaft is large, then we will have our tightest fit. So this is our lecture, and in the next lecture we will be discussing some standards that are related to the hole and shaft fits and how we will use them to actually put dimensions on our holes and our shafts.